Subnetting is one of the most important CCNA skills. And in this lesson, you'll learn a fast four-step method that helps you solve IPv4 subnetting questions with confidence instead of memorizing giant tables. Early IPv4 addressing used fixed classes. That made networks easy to label, but it also wasted huge blocks of addresses when an organization needed something between the size of a Class C and a Class B. As more organizations needed medium-sized networks, Class B space disappeared quickly. CIDR fixed that by allowing variable length masks, so networks could be sized much more precisely. An IPv4 address is 32 bits split into 4 octets, and each octet follows the same bit values from 128 down to 1. Once those values feel automatic, subnetting gets much faster. For speed, practice converting small numbers in your head. 26 is 16 plus 8 plus 2, so its binary pattern is 000111010. That's the kind of quick math CCNA questions reward. A subnet mask is just a row of consecutive ones followed by zeros. The ones mark the network portion, the zeros mark the host portion, and slash notation simply counts how many network bits are turned on. If you line up the IP address and the mask in binary and apply a bitwise AND, the result is the network address. That's why a /26 becomes 255.255.255.192 in dotted decimal. You don't need a giant chart. For /24 through /30, memorize 3 things for each prefix: the mask, the block size, and the usable host count. Once those patterns are familiar, you can answer most subnetting questions by recognition first, then verify with the method. Now we get to the shortcut that makes subnetting feel manageable under pressure. The magic number method gives you a fast way to find subnet boundaries without guessing. Start by finding the interesting octet. That's the octet where the mask is neither 255 nor 0. Then subtract that mask value from 256. The result is your magic number, or block size. For /26, the interesting octet is 192. So 256 minus 192 gives 64. For /27, it is 224, so the block size is 32. Those numbers tell you where each subnet starts. Let's subnet 192.168.10.0/24 into 4 equal networks. To get 4 subnets, borrow 2 host bits. That changes the prefix to /26. A /26 gives a magic number of 64, so the subnet networks are 0, 64, 128, and 192 in the last octet. Each block runs up to the address before the next subnet begins. That means the first subnet is 192.168.10.0 through 63, with hosts from 1 through 62 and broadcast at 63. The same pattern repeats for the other 3 blocks. With 172.168.1.0.200/27, the block size is 32. Count by 32 in the interesting octet until you bracket 200. The block starts at 192 and ends at 223. So the network address is 172.16.45.192, the broadcast is 172.16.45.223, and the valid hosts run from 193 through 222. That's the exam pattern you want to recognize fast. To find usable hosts, take 2 to the power of the host bits, then subtract 2 for the network and broadcast addresses. A /26 has 6 host bits, so 2 to the 6 minus 2 gives 62 usable hosts. For prefixes from /17 to /23, the interesting octet often moves into the 3rd octet. That changes how you count because whole 4th octets now sit inside each subnet block. Take a /22. The mask is 255.255.252.0, so the magic number is 4 in the 3rd octet. A network that starts at 172.16.4 .0 runs all the way through 172.16.7.255. Real networks almost never need every subnet to be the same size. That's where VLSM comes in. And it's the technique that turns subnetting from theory into design. If every subnet is the same size, small segments waste addresses. VLSM fixes that by letting you assign different masks to different parts of the same network based on real host needs. To use VLSM, your routing has to be classless. Protocols like RIPv2, IGRP, OSPF, and ISIS support it. And when you design, always allocate the largest subnet first. Start with 172.1.6.0.0/16 and sort the requirements from largest to smallest. If one LAN needs a /26, place that first so it gets the first available block. Then continue from the next open address with the /27, /28, and /29 networks. Each new subnet begins at the next valid boundary for its own block size. Finish with /30 links for point-to-point WANs. Largest first keeps the plan efficient and prevents a small subnet from blocking space that a larger one needs later. Before we leave IPv4 addressing, you need to recognize the private ranges instantly. They show up everywhere in enterprise networks, home labs, and CCNA questions. The private IPv4 ranges are 1.0.0.0.0/8, 172.16.0.0 through 172.31.255.255, and 192.168.0.0/16. These addresses are not routed on the public internet, which is why NATA matters. Also know the special ranges. APIPA is 169.254.0.0/16, loopback is 127.0.0.0/8, and multicast is 224.0.0.0 through 239.255.255.255. They are common clues in troubleshooting. Now let's move from planning addresses to putting them on Cisco interfaces, because the CCNA expects you to understand both the math and the device behavior. On a Cisco interface, you'll enter the IP address, the subnet mask, and usually a description so the link is documented. Then you apply no shutdown to bring the interface administratively up. That last line is a classic trap. A correct address with no shutdown missing can still leave the interface unusable in a lab or exam scenario. Use Show IP Interface Brief for a fast status view, show interfaces for detailed counters and line conditions, and show IP route to confirm the network is actually present in the routing table. Remember the status language. Up means working, down usually points to a physical or signaling issue, and administratively down means the interface is shut. CRC errors often point to a bad cable or layer 1 problem. Knowing the method is only the first step. To use it under exam pressure, you need repetition until the patterns become automatic. Over the next 30 days, drill binary values, mask recall, and magic number calculations first. Then move into full subnetting problems and VLSM design once the basics feel quick. A good benchmark is solving common /24 questions in well under a minute, and third octet problems like /22 in a couple of minutes without losing accuracy. Watch for the common traps. Students often pick the network or broadcast address as a host, or confuse the number of subnets with the number of usable hosts. Also remember the edge cases. /31 and /32 behave differently, and VLSM only works correctly when the routing environment supports classless forwarding. You now have the core pieces that make IPv4 subnetting practical. Binary masks, magic numbers, host counts, VLSM, private ranges, and iOS verification commands all fit into one exam-ready workflow.